as you mentioned, CCF is a well-known method to deal with climatic loading and a couple of other issues in double-layered facade. What's so special about this project is mainly the geometry we talk about and the air volume. You can see here, it's a part of the facade. It's a round tube. The tube has a diameter of 900 millimeters and a length of 9 meters. This was a project engineered by Eckersley O'Callaghan in London and New York. The architects were Saul Ill, Roland Ill, and we installed the facade and manufactured the pieces. So this is the overall facade. It's a high-rise building in Hong Kong. We have 238 tubes between a length of 4 meters and 9 meters. As I said, the diameter is 900 millimeters. So there's quite a lot of air in this tube. And most of these tubes are not full tubes, it's just a half tube and they are open, just basically a facade. But in certain areas, the building owner also wanted to close it with a better building physical performance. So it's a full tube, 64 full tubes. So we have 2 half tubes bonded together, and also half tubes where we have a curved glass and then a flat glass bonded to this one. It's all annealed slumped, 2 times 10 millimeters or 2 times 12 millimeters, depending on the cross section, and laminated with sentry glass. From a structural point of view, this was one of the most complicated points. This pole frame, very big pole frames, and the weight of these tubes is quite significant. It's about 1 to 1.5 tons, depending on the length. So we have a couple of tubes here in this entrance area of this portal frame, and one of the first ideas was to hang it and then have a transfer beam to transfer the load in the adjacent tubes. But in the end, we made this portal frame thicker. So this portal frame looks quite slim, but it has a thickness of 80 millimeters, and it's 900 millimeter deep. It's a duplex stainless steel with a strength of 460 MPa, so rather massive. And the first challenge, we were not yet involved in this phase, but Ferran, you were, I think. The first question was, can we build this glass? Is there a company out there who's able to manufacture this glass? And I think you were approached by Eckersley O'Callaghan. Can you build this? And you build a prototype. It can still be seen at your facilities, right? It's still out there, 900 millimeters. It's a half tube. And one of the main challenges is the tolerance. So it's slumped, annealed, and this was one of the quality control measures. So a general problem of curved glass is the flat edge. So always in the areas at the right or left, it's 10 years ago it was typically about 200 millimeters flat, and here it's a very, very small area. And especially if you bond these two together to a full tube, you need almost a perfect geometry. So when this was confirmed that we can, when Precursor can produce these kind of glass, Eckersley O'Callaghan took on with the engineering of the project, and they also helped us to push this through the building department in Hong Kong. So in Germany, it's already not always easy to deal with the building authorities, but in Hong Kong, it's even more challenging, let's say, and you need not only excellent engineering skills, but also you need to communicate in the right way. You have to find the right words to convince the building authorities that this is a project and a facade fulfilling the requirements. And there we got great help from Eckersley O'Callaghan. And in Hong Kong, in Germany or in Europe, the typical wind load is about 80 to 120 kilogram per square meter. In Hong Kong, the wind loads are much, much higher, between 260 and 400 kilogram per square meter. And especially in the opening areas, the blue here, we have loads up to 5.1 kPa, both suction and pressure. And in the end of I will show some pictures afterwards, there was a very high hurricane, and so we have these very high wind loads acting on the facade. Interesting here from a structural point of view is the interlayer. This is all laminated with sentry glass for a couple of reasons, but in this case not due to structural reasons. Because let's say we have 3 kPa on a 2 times 12 millimeter, or we have to half the load on half the thickness. If it would be a flat glass, you would double the stress and you would get 4 times the deflection due to the moment ratio. But because we have a very high, very stiff cross-section due to the geometry of the curved glass, there is no significant effect of the interlayer stiffness. And the main stresses are also the glass edges. So this requires a very sensitive manufacturing of the glass edges, a high quality polishing. And the stresses in this preliminary calculations are about 10 MPa, but finally the glass stress utilization was about 99%, because we do not only have a symmetric wind load, but also some asymmetric wind loading, some combinations of the wind. So there's a lot of stress in this glass going on. But now I would like to concentrate on the closed cavity technology we put in there. So as I said, this is not a classical double-layer facade system where you typically have a space of 100 to 300 millimeters. The volume in this air, the air volume in this cavity is typically between, depending on the size, between 500 and 1,500 liters. In this case, due to the diameter of 900 millimeters and the length of 9 meters, it's an air volume of roughly 5.7 cubic meters, 5,700 liters of air. And you need to prevent condensation in this cavity. And another issue is the climatic loading. We discussed a couple of times this morning. So if this air, if you heat up, say 6,000 liters of air, it expands by about 800 liters, so roughly 10%. And this air is expanding and wants to get out of this, this cavity. But if you cool it down, it attracts air from the outside, and this is generally, especially in Hong Kong, quite humid. So the risk of condensation in the cavity increases. And if the cavity is sealed, you get very high climatic pressures. And these are an issue for both the glass and also the silicone connecting the two glass tubes. So we needed to depressurize this air volume. So basically it's an open system. From the top, we blow dried, tempered, and cleaned air into the air volume, and we extract it. So there's always a slight overpressure in the system. And the question is, how many air do we need in the system to prevent condensation? Of course, you can. So as I mentioned, it's about 6 cubic meters. You don't want to exchange it every hour, because this would need a lot of energy to exchange the air. So the question is, we wanted to minimize the airflow through the system. At the same time, we wanted to minimize the energy consumption of the overall system. But also all the machinery behind it, the diameter of the CCF system had to be minimized and optimized. And how did we tackle this one? So we did a climate analysis for Hong Kong, which is completely different to Germany. We did a temperature study of the different tubes, and we looked at different airflows through the system. Let's first take a look at the full tubes and half tubes. So again, the full tube on the left. So these are the geometry we just saw, and they are bonded together. So here they are bonded together with silicone, so it's a closed cavity. And the half tube is very similar, only that the back side is a flat glass, and we only have 5 of them and 64 of these. And this is mainly because there's a concrete wall behind it. So it was because the change of the geometry is only meant to the space available. But in principle, it's the same technique. Interesting though, the half tube reacts quicker than the full tube because it's less air in there, and also there's a reflective some kind of reflective coating here in the back. So we get, you see here a typical 2-day period, not very extreme conditions, but normal temperature conditions, maximum temperatures of 25 to 30 degrees. For the long-term testing, we observed temperatures up to 50, 55 degrees in the system. So here, a medium range temperature. But you can see that the temperatures in the half tube the the temperatures get, where's the pointer? Yeah. The temperatures get higher here. But let's now look at the temperature, at the climate conditions in both Germany and Hong Kong. What's different? As you know, Germany is much colder than Hong Kong. In Germany, we have an average year temperature of about 8 degrees. In Hong Kong, 22 degrees. So much, much warmer, and also much more humid. There's much more moisture in the air in Hong Kong, which is a challenge for the CCF system. But the absolute temperature or the absolute humidity is not really an issue. The issue for the system is the change of these parameters, because it's a dynamic system. So at the top, we have a diagram of the temperature drops, the temperature increase to the right, and the temperature drop to the left. And the critical thing for this air volume in the tube is a sudden decrease of the temperature. So imagine you have this 6 cubic meters of air in the tube, and then suddenly the temperature goes down from, say, 60 to 20 degrees, or from 30 to a very quick decrease. Then you still have the same moisture in the cavity, and the temperature approaches the dew point temperature, and you have condensation. So in Germany, here shown in brown, we have much more significant quick temperature drops in comparison to Hong Kong. So Hong Kong, mainly, we have very slow change of the temperature. It's almost very constant, and the changes of the temperature are rather slow. In Germany, the average temperature is lower, but the changes are quicker. So in Germany, it would be this sudden drop of the temperature is a critical issue. Whereas in Hong Kong, it's mainly the amount of moisture, the humidity in the air, which is an issue. And one parameter to look at this is the partial vapor pressure. So if the partial vapor pressure, it's the pressure of all the molecules of the air, of the water molecules in the air, approach the saturation vapor pressure, then we get condensation. And this relation between partial vapor pressure and saturation pressure is also called relative humidity, and depends again on the air temperature. So the higher the temperature, the more humidity can be in the air. And what's interesting here to notice is this one here in Hong Kong. So there is not a significant drop of the temperature, but a sudden increase of the vapor pressure changes. And this is so there's much more humidity in the air in Hong Kong, which is the reason why you generally need more controlled conditions for the CCF system. And this is the reason why we took the air from the inside of the building, from the conditioned air from the inside. We generally have a very constant humidity of 60% relative humidity at a temperature between 20 and 24 degrees. And then we looked at, okay, how can we minimize the airflow through the system? And by minimizing the airflow, we also minimize the energy consumption of the system, but we also minimize the diameters for all the stainless steel pipe systems we needed. In general, we have an east facade and a west facade, as shown in the beginning, and they are controlled independently by 2 independent systems. And of course, you want to minimize any permanent costs. So, and at the same time, prevent condensation. So, 6,000 liters of air in this tube, and if you see here 3 diagrams, and this is the first one is in an airflow of 720 liters per hour. It's a rather quick air exchange. The medium one is 120 liters per hour, dried, tempered, cleaned air. And the last one is a very slow airflow of 20 liters per hour. And then you see on the horizontal axis the temperature range, which is the temperature difference between the cavity temperature and the dew point. And the dew point depends on the humidity and the temperature of the glass. So the bigger this gap between dew point and temperature, the higher the safety level against condensation. And generally, we need a safety level of 3 Kelvin between dew point and temperature. So for example, at the bottom, 20 liters per hour, so a very small air exchange. A lot of, and then we measured, this is over 1 year, numerical analysis, tested, and we measured the temperatures, and these are the counted values. And you see a lot of values in the range between 0 and 5 degrees, which means that the temperature is very close to the dew point, and we could also observe some slight condensation in the tubes. So it was clear we need to increase this value, although we started with the higher values and then went down, of course. And with the other extreme is, the other extreme is 720 liters per hour, shown at the top. So there, the temperature difference between dew point and cavity temperature is generally very high, at least 15 Kelvin, up to 20 Kelvin or even more. So there's a very high safety level against any condensation. And then we also tested an intermediate value of 120 liters per hour. And there you see a more even distribution. But also there's not a single count below 5 degrees temperature difference. So this gave us quite a confidence to set this airflow between 200 and 300 liters per hour with a certain safety level in the system. But you're also able to adjust the airflow in a certain range. But then you're basically depending on the diameter of the whole system and on the power of the CCF system. But if you build these together, if you build this you want to build it in a clean room with safe conditions, and then you have to transport it and you have to install it. And this is generally also a critical time because you need to condition the air volume. So you have to prevent any dirty substances, and the air is not clean. It's relatively dirty. You have to prevent the air from entering into the cavity. And if you have temperature changes, it's cooling down, as I said, it's expanding or contracting, and it's attracting air. So you need to condition the cavity also during transport and installation. And this is the reason why we built these tubes in Hong Kong. So we set up a clean room in Hong Kong. The glass was produced in Europe and then shipped to Hong Kong. And the CCF tube elements were manufactured and assembled in Hong Kong in a clean room. Then we had a large storage space there. And then it came to installation. And due to the bending radius of 450 millimeters, you cannot use a normal glass sucker. So we needed to develop a special glass sucker which is able to work with these tubes, which was successful. And then we were able to install these tubes by tube. And there's basically a silicone profile between these tubes and also LED lighting. So the building owner can play with the light in the joints and illuminate the facade. So we started the installation in January 2017. It took about a year to install most of the tubes, and another half year to do all the rest work. And then there was a big, and the culture is also again different in Hong Kong than in other countries. So this is a typical bamboo scaffolding, and it's interesting to see. It's a different culture, but it finally worked well. And here on the right side, you see the part of the tube facade. It's basically here on this level, and here on this level, and there's an entry. And then, as I said, we had very high wind loads, up to 5 kPa in Hong Kong. And there was a big typhoon in August 2017. We almost installed everything. And there was a lot of glass breaks. So if you read the newspapers or look on the internet, there were a lot of glass breakages all around Hong Kong after this typhoon. And also the scaffolding, it's bamboo scaffolding. Not every scaffold performed well. But fortunately, the glass performed as expected. And I'm happy to answer any questions. Thank you.
Any questions?
Hello, a very exciting project and a very exciting example of CCF. Could you say what about the costs per square meters for such a construction?
I'm a technical guy. There's the. Heiko, you want to say something?
It was absolute special, very expensive.
Okay.
Very expensive.
Comparable to any CCF project.
No, I think this has not been done before in this kind of volume, in this kind of shape. So it was expensive, yeah. Peter?
Was it the right solution?
Sorry?
Hong Kong? Was it the right solution, the CCF for Hong Kong?
What is your what else do you want to propose?
You're asking.
We have another system here, but this is another topic. Heiko is presenting it tomorrow.
Yes.
With a desiccant system. So there are other opportunities out there too. And another idea is to have a desiccant in the cavity to absorb the humidity. But I think due to the geometry and the amount of air we have there, CCF is the right system, yes.
Can I ask a question about the wind loading, please?
Yes.
You have a very complex arrangement of buildings there. You also have curvature in the facade. So did you do wind tunnel tests to establish the...
That were one of the main discussions also in the beginning. I think, James, you were also involved in this. And we conducted wind tunnel tests to get also the wind load distribution on this geometry, yes. It was a big topic.
Thank you.
Hi, Martin. Just a quick question. Why did you end up shipping the pieces, the glass of the IGU, to Hong Kong and then assembling it there, rather than sort of attaching it to a breather system or a desiccant system for transit and manufacturing it in Germany?
It would also be possible, but mainly to have it to minimize the air to minimize the time frame where we need to condition it. We want to minimize this, and this is the reason why we assembled it in Hong Kong. Could also be done in Germany theoretically.
I have a question about the thermal stress. If I got it right, you used annealed glass. It was not tempered glass.
Yeah.
Of course, you made laminated glass for safety. But what about thermal stress? You used any coatings which increase also the risk of?
So luckily there were no coatings, I think. No coatings, no print on it. So it was clear glass, and there is no dark object behind it. So we do not expect very high thermal stresses in the glass.
Okay, thank you.
Can you tell about the replacement strategy of these pieces if for any reason one breaks? How many parts you have to take apart?
You can take each one apart, so that they're not bonded with each other, but there's basically a kind of a gasket, and it's a silicone aluminum profile and a gasket between, so you can take out each element by its own, which makes replacement quite easier. Thank you.
Hi there. Did you like what you just saw? If you did, why not like the video? Drop us a comment below, as well as share the video with others, since GPD is all about sharing. And to receive more videos in future, subscribe and don't forget to click the bell icon for notifications. Ciao.